Okay, I think it's time to start. Welcome everyone to this seminar on how well can we predict chemical toxicity using AI-based models. Um, this is a seminar arranged by FRAM, the Center for Future Chemical Risk Assessment and Management here at the University of Gothenburg. It's a multidisciplinary center. So I have asked today's presenter to be mindful of the diverse backgrounds of people attending. But great to see so many participants here. As you have seen, we are recording this seminar and it will later then be put on the FRAM's homepage. We will not record the final discussions, etc., but just the presentations. My name is Daniel Slunge. I'm the director of FRAM, and I will moderate this seminar. Okay, so we have two presenters today. We'll start with Styrbjörn Kjell, who is a PhD candidate at Chalmers. He will present on predicting chemical toxicity across eukaryota. And then we have Patrick Svedberg, who will make a little shorter presentation. He's also a PhD candidate, but at the University of Gothenburg. And he will speak on prediction biases in quantitative structure-activity relationship models. So without further ado, I'll leave this over to Styrbjörn, and he will present for around 25 minutes, and then we'll have time for one or two questions for clarifications, and then Patrick will present, and then we will have more time for questions and discussions. And you're, of course, welcome to put questions and comments in the chat meanwhile the presenters speak. Okay, welcome, Styrbjörn.
So yes, thank you very much for inviting me to speak today at this webinar. So my name is Styrbjörn Kjell. I'm an industrial PhD student at the Department of Mathematical Sciences at Chalmers and at the company called Planetary Group. And today I'm going to talk about this Trident 2, which is a recent model that we have developed at Chalmers, where we aim to predict chemical toxicity across eukaryotic organisms. So I hope this will be on a good level for everyone to understand, but please ask questions after if you didn't catch everything. So we will begin here by showing this iceberg, which I'm sure many of you recognize. So basically, we know very little about chemical hazards in general. And it's illustrated here by this iceberg to the left, where we see estimates of the number of chemicals on the market today. So here they estimate roughly 100,000 chemicals in total on the market. This is a figure that is a bit wrong in my opinion, but we are probably closer to 300,000, but it's fine for educational purposes. And on the very tip of the iceberg here, we have 500 chemicals that are extensively characterized for their exposures and hazards to both humans and to the environment. But then we see the numbers rapidly increase, and below the surface here, where we have risks that we currently are unaware of, we can think we have almost 90% of the chemicals that basically have very little data about their hazards and exposures towards the environment. So we can conclude this, that chemical hazards are poorly characterized. Also, on top of this is not static numbers. They are rapidly growing, actually. There are estimates showing that the market is growing like 4.4% each year. So this is a growing problem as well. Typically, we try to fill this data gap by doing animal exposure tests, where we basically expose different animals to these chemicals and check if they die or not. This is the way we have done historically these risk assessments, but this is, of course, time-consuming and very costly. So we need new ways of filling in these unknowns, and this is what people in my field are working with. On the positive side, databases on chemical risks or chemical hazards are growing rapidly as well. So we have a lot of data out there that we can use to build computational models instead of doing these animal exposure tests. So that's what we are doing in this project. And this transition from going from exposure tests to doing what's called new approach methods like computational tools is not only an initiative from the scientific community, it's also an EU initiative, actually. So just to remind ourselves what we are talking about, so here we see some poor fish living in aquariums whose fate is to die. But this is, of course, a very difficult process, and it takes a lot of time, as I mentioned, and it costs a lot. It's ethical. But on top of that, it's also problematic because we can only do this for a very small number of organisms. So we call these model organisms. I don't know, we use roughly a handful of standardized test species to derive these risk assessments. And that is also very problematic because, of course, biodiversity is much broader than a couple of model organisms. On the other hand, these new approach methods, like these QSAR models that we and Patrick is going to talk about now, are good alternatives, but traditionally they have suffered from quite poor accuracy and a very narrow applicability domain. So you can't really use them for a lot of chemicals out there. So our idea is to instead use AI-based methods here. So we can consider a hypothetical case in which we have 10,000 species, for example, and 100,000 chemicals. This would need 1 billion animal exposure tests to cover. And that's, of course, completely unreasonable. So this also is just a way of illustrating that we need new ways to estimate these hazards. So now I wanted to briefly spend a minute on talking about why we need AI to solve this issue. So one can contrast the two sort of paradigms to do computational methods with these two figures here, white box models in comparison to black box models. And a white box model is how traditional QSAR methods have been done. So these are based on explicit assumptions about our data. Basically, we know what we need to know. And we have traditional statistical methods like linear regression and logistic regression. On the other hand, black box models, we make very minimum assumptions about the data, basically assuming that we don't know what we need to know. And herein falls AI and machine learning methods like neural networks and language models and so on. They have both pros and cons. White box models are good because they are easy to interpret and explain, but they suffer from low performance on complex data. Whereas black box models are very good at handling complex data, but harder to interpret. The iceberg, however, falls into this black box situation because toxicity in general is very poorly understood, especially if we look at the whole picture, like many species, many chemicals. We need AI-based models to basically solve this problem. Because the white box models, we can't make any assumptions about the data that will make them work for every chemical species. So good, that's out of the way. So what is our approach to toxicity prediction in this case? Let's illustrate it here to the right, very simplistic. We have a chemical structure. We want to build a model that can take some toxicological metadata about the experimental setup and then predict sort of discrete values along a dose response curve. And a dose response curve is, of course, where we have the dose of the chemical on the x-axis and then basically the fraction of the population that has shown some toxic effect to this thing. So we want to develop a relationship between the chemical structure and its toxicity. And this relationship needs to be inferred from data containing results from animal exposure tests. And we will then use AI to increase the predictive performance in comparison to these other QSAR tools and expand the applicability of these computational methods so that we can fill these data gaps. We have actually already done something like this. We did it with something called Trident 1, which is the predecessor of Trident 2, where we did toxicity prediction for aquatic species groups. This was published in a paper in Science Advances 2 years ago. And the figure here illustrates basically the model error when we compare Trident 1 to 3 very common QSAR methods that are used widely today. And as you can see, Trident, being the lower bars here, is vastly more accurate compared to these other QSAR methods. So this had high potential. And Trident was structured roughly like this. We subdivided it into 6 individual AI models. They targeted various proportions of the data or strata of the data. So we had some fish models, some crustacean models, and some animals. We got predictions on the species group level. But one can argue that this was quite stupid. I mean, why do we even want to estimate the toxicity of species groups? What is a species group? It's a very vague human concept. So what we want to do now with Trident 2 is we want to extend this to predict on the species level for both aquatic organisms and for terrestrial organisms. And we also want to do this with a single model, because the idea is that a lot of these toxicity behaviors that we see can be extrapolated between both species and chemicals. So we can actually learn something from training on all the data simultaneously. So this is the goal of Trident 2. And again, we have some chemical structure acting as an input, but now we then also want to teach the model something about taxonomy. And the reason we add taxonomy here is because our assumption is that basically species that are taxonomically similar to each other, that is how evolutionary similar they are, will behave approximately similar. But I also want to point out that since this is AI methods, the model can also choose how to use this taxonomic information. So it's not necessarily the case that it will use it the way we think it will. So speaking of data, when we train AI models, we need data. So perhaps the most important result actually from what we've done until now is getting the data and harmonizing the data. So to remind ourselves, this is the data we are working with. It's animal exposure tests where we have dose response curves or discrete points along a dose response curve. We have gathered approximately 500,000 whole animal exposure assays, and these encompass roughly 7,000 species and 80,000 chemicals. It's divided like this in this pie chart here to illustrate that we have a lot of ecotoxicity data, that is data for aquatic organisms and terrestrial organisms. But then we have a quite large proportion here that's also made up of mammals, which are treated in a bit separately. So that is experiments on mostly rodents. And if we look a bit further into this, here we see the number of unique chemicals that we have for each species group. And as you can see, rodents are vastly overrepresented. So we have almost 80,000 chemicals for all the rodents, whereas the remaining species groups are way lower. But still, it's a lot of data, so that's very nice. And we can look a bit further into the data sets. So this is the case, unfortunately, that the data is very diverse, but it's also extremely skewed. So what we see in the leftmost figure here is the number of observations we have in the data for different chemicals. So here we have some copper salt that's been widely observed. But then we see in the tail end here, we basically only have one single observation here. So it's a very long tail, this distribution. And the same is true for the species. So we see mice and rats being overrepresented, and then we have a couple of strange species down here that are the same observation. So this is an inherent problem with the data, just to let you know. And the final data slide here, I just wanted to show the sort of taxonomy of all the species that we have. So it's a very broad range. We have everything from cyanobacteria, which I know is not a eukaryotic organism, but we kept it anyway, all the way to the mammals down here. So very broad distribution of species. And you can also see the number of species and genus and families and orders and so on here. So it's a very interesting data set. Good. So now I thought I'd spend a couple of slides speaking about the model, because a lot of work goes into building this AI model. So again, we want to predict chemical toxicity for eukaryotic species. And we are actually borrowing techniques from natural language processing here, and specifically large language models like ChatGPT, to interpret this data. So what we have here is the chemical structure, of course. This is the input to the model. We also have the species, in this case, the rat, the exposure route, that is how was the chemical administered to this rat, the life stage of the rat, how long it was exposed, and also which toxicological effect we are going to estimate. And this enters what's called a transformer. And a transformer is this core component of large language models. And it's very, very good at finding complex patterns inside complex data. So that's the reason for choosing it. And from this transformer, we then predict these 4 values, which again are discrete points along the dose response curve. So that's very briefly how it works. We can look a bit deeper into this. So the chemical is represented by what's called a Smiles string. And this is actually analogous to representing text as words, tokens. This inside the transformer is given numerical high-dimensional vectors. That's illustrated here. And the transformer interprets these vectors to then derive a single sort of numerical representation of the chemical. The same is sort of done for the taxonomy. So we have the tree representation, that is how are all the species related to each other. We then do something called a multi-dimensional scaling of this tree, and we derive the same numerical representations of the species. And what's interesting here is that the distances in this numerical space is the same as the distances in the taxonomy tree. And this then is turned into a single vector representation of this zebrafish. What then happens, and this is the most crucial step, is that both of these numerical representations are treated inside the transformer. And the transformer then makes a single numerical representation of this combination of both chemical and species. And this is what is used to predict the toxicity through it. So that's a bit more detailed what happens inside this big black box. So now I thought we'd look a bit into this numerical representation. So this is the first result slide. So actually this numerical representation is a 768-dimensional vector. That means that each combination of species and chemical gets a vector of 768 dimensions. And we can project this using something called principal component analysis down to 2 dimensions. And each point in this plot that we see here is a unique combination of chemical and species. And in this case, this point here is rotenone, which is basically a hazardous chemical towards fish, where we have exposed it to rainbow trout. The color is the experimental LC50 value. So this is the value that you would arrive at if you were to do an experiment. And what we can see is that the model manages to then separate non-toxic combinations up here from very toxic combinations. And it also places them along a very nice sort of toxicity gradient here. So this shows, in my opinion, that the model has learned something about toxicity, which is very nice. But of course, we need numbers to estimate performance, not only visuals. So what we are looking at here is instead a bar plot, where the bars indicate the median absolute errors. So that is when we compare the model's predictions to experimental data. How good are these predictions? So what can be said is that in general, it performs very well. You know, the numbers probably don't tell you much, but we can compare it to just guessing the average within each species group. And then we would end up with this line here. And since the bars are way lower than this means that the model has learned something from this thing. So the takeaway from this bar plot is that the model is quite accurate and it's very stable across all these various species groups, which is interesting. We can also compare the applicability, which was something we talked about in the beginning. And that is where we basically check how many chemicals can we predict inside this data set. We compare this to other tools that are out there. So here we compare our model, Trident, to 3 different QSAR models that are very common to use inside our field. And the numbers, the bar chart here, shows how much percentage of the data that we can actually predict using these different ones. And Trident, being sort of chemical agnostic and treating chemicals as strings, can predict anything, basically. Whereas you see these other tools are suffering a lot. And in some cases, they can't predict anything, and in some cases, they can predict roughly half. So this is, of course, a very important result. So basically, the model can predict anything. Now I wanted to show an interesting result. So here we look at the same errors that we had in the previous bar chart, but only for one particular point on the dose response curve. So this is again the model error. Then I'm adding these diamonds here. And what we are now looking at is when I've only trained a model on only one species group. So the diamond here is when I've trained Trident 2 on only worms, whereas the bar is when I've trained Trident 2 on all these different species groups. And since the error is much lower, the bar is lower than the diamond, this means that the model gains information by training on many species groups simultaneously. And this is, in my opinion, a very interesting result. So now we can ask ourselves, what can we do with this model? This is very interesting. So what are the possibilities? So if we again consider this huge taxonomic tree spanning almost 7,000 species, now let's predict stuff for all the species. So it can look like this. We can take a single molecule, like bromazine in this case, which is a known herbicide that disrupts photosynthesis. And we can predict the toxicity for all these different species. And the bar height here for all these leaves in the tree reflects how hazardous the chemical is. So basically a red bar indicates that it's very hazardous and a green bar that it's somewhat okay. And what we can see then for bromazine is that it is very toxic towards these green parts in the tree. And this is the plants and the algae. So this makes sense because plants and algae do photosynthesis. So it makes sense that bromazine will be hazardous towards these groups. Also, we can see that it's actually hazardous towards this sort of turquoise group here, which is the cyanobacteria. And that also makes sense because cyanobacteria also do photosynthesis. So it makes a lot of sense. And we can stack other chemicals on top of this bar plot. So here we see thiamethoxam, which is a neonicotinoid or an insecticide. And then we see red bars popping up along this purplish part in the tree. And this is the insects. So this also makes a lot of sense. We also see the green bars. They are mostly here for the other vertebrates, like the mammals and reptiles and so on. So these are not as sensitive towards this. And the final one I will show is a chemical called rotenoan, which I showed you previously in the PCA plot. And here we see fish standing out as the very most sensitive species group. So here we have the bars, but we also see a lot of yellow bars. So rotenoan is actually very hazardous towards a lot of species. So this is, in my opinion, a very interesting way to look at all this data we have available. So with that, I'm on to the summary and conclusions. So again, this was what we set out to do. The hypothetical scenario of having 10,000 species and 100,000 chemicals becoming 1 billion combinations. And our goal was to use AI here. So what I hope I have conveyed to you now is that AI-based methods have the capability to improve computational toxicity prediction compared to these other QSAR tools. Also that predictions are reliable enough for a lot of species so that we can use them for hazard assessment or risk assessment. And also, I want to again stress the fact that, I mean, it's completely unrealistic to fill this data using animal exposure tests. I also want to point out that methods like this make use of all the data that we have out there. So we have data from regulatory frameworks, we have from the scientific community and so on. So this is a very sort of good way to use all this data. I think this is important to point out. Also, new models for chemical toxicity prediction are published every day. But my own personal opinion is that to reach higher performance, we might not need new models, we need new data. So this will only get much better if we can deploy it. So future outlook, what's happening in my world now? I'm going to publish this new methodology, hopefully. And then I'm going to publish a new version of our website, which is free to use. So we have a website for the previous model, Trident 1, where any user can predict completely for free the EC50 and the EC10 values for any chemical they like, for aquatic species groups in this case. But the new model, we will, of course, add a lot more data into this database. Our goal is to, in the end, build some sort of system that users can use to interact with all of this data, get access to this. We also have a pilot project where we are basically checking if we can use in vitro bioassay data to improve these predictions. It's very interesting. And then to end with, I have a final question, an open question really. That is, if we can screen any chemical across all these species, what should we do with it? How would this impact our way of doing chemical risk assessment? So just food for thought. And with that, I say thank you. I'm on 25 minutes exactly, so that's good. Thank you to my collaborators, my supervisors, Mikael and Erik, of course, our funders, and NICE for lending some nice compute power to this project. Thank you very much.
All right. Thank you for inviting me to speak here, and thank you, Styrbjörn, for your excellent presentation. I'm going to talk a little bit about prediction bias in quantitative structure-activity relationship models. Styrbjörn mentioned it, but I'm going to go a little bit into detail about it. And this is a project that I've been doing with my supervisors, Pedro, Thomas, and Mikael, but also with Erik, as mentioned before. And I want to start with this quote. It's actually celebrating 50 years today, or this year. All models are wrong, but some are useful. And that all models are wrong, of course they are by nature. They are model representations of something else. What I'm interested in this project is how they are wrong, what types of wrong they have, and that is what determines their usefulness. And the models we are talking about, as I mentioned, are these QSAR models. And just to recap a little bit, they predict an activity or property based on some sort of descriptor or structure of a chemical. And as we saw in the previous presentation, they can be built using machine learning techniques, but also more simpler traditional linear regression. And they have seen wide use in the pharmaceutical industry, especially drug development, but also more recently in ecotoxicology. And for us in ecotoxicology, we use these models to fill data gaps. For example, when doing risk assessment, but we can also use them to screen for compounds that seem to be the most toxic, or screen for compounds that needs to be prioritized for testing. And we are allowed to use these when we are registering under the REACH regulation. Not solely predicted values, but they can be used as a sort of weight of evidence approach. And the key question we started out this project asking is, how well do these QSAR models perform for ecotoxicity prediction? And we looked at 3 models, and you will recognize if you had a keen eye on Styrbjörn's graphs. We looked at EcoSAR, the Vega Hub, and toxicity estimation software tool. The first and last of these are developed by or have been developed by the US EPA or subgroups therein, and the Vega Hub is developed by a group in Italy mainly. They were chosen because they are freely available, high throughput models, and they have endpoints relevant for current chemical regulations. And these endpoints are acute and chronic toxicity to microalgae, Daphnia, and fish. And if you again have had a look at Trident 1, then you will recognize the microalgae and the Daphnia, meaning aquatic invertebrates and fish. However, TST is only available for acute Daphnia and fish, but it will still be in our comparison here. Before we get to the results, I will just quickly want to show you how this system is set up or how our comparison is set up. We started with empirical data. We used the largest freely available ecotoxicity set from the US EPA. We did some pre-processing, filtering down of the data. We used reference information from the OECD guidelines and collected identifiers where they were needed from PubChem and WebChem. And this was our empirical data set, our comparison data set, if you will. And then we had our models, the EcoSAR, Vega, and test. We put these identifiers, the smiles, as mentioned before, into the models. We did some post-processing, and we had our predictions. We also added some physical chemical information from our reference information. I'm not going to talk about that a lot today, but it will be in the final publication a little bit about that. But we started out with almost 13,000 compounds in our empirical data set, but then we removed everything where we had no OECD guideline data, basically. So any chemical that had at least a value for acute or chronic algae, Daphnia, or fish toxicity tests were kept. Then we removed all non-organic compounds because these models explicitly tell us that they predict organic compound toxicity. We removed compounds with very high log KOW, meaning lipophilicity, or low water solubility, because they are also known to be problematic in these cases. Finally, we removed the ionizable compounds, so we didn't have to worry about what pH the tests were performed at. And we ended up with around 1,800, a little bit less than 1,800 compounds. And in cases where we had more than one empirical data per compound and species and time frame, we used the geometric mean to calculate the value. Finally, the QSAR predictions, the post-processing I mentioned. For EcoSAR, it meant removing baseline toxicity, the baseline model, if we had more specialized model predictions, completely in line with EcoSAR user instructions. We removed any empirical or training data from test and Vega because we do not want to compare empirical data to empirical data. We want to compare the predictions to empirical data. And finally, we removed predictions that were deemed outside of the applicability domain. Styrbjörn mentioned the applicability domain, but it's basically the chemicals for which the model itself is applicable or gives a reliable prediction. And then again, we took the geometric mean if we had multiple predictions from the same model software. For example, in Vega, there are 6 different acute Daphnia models. So if we had multiple models within the applicability domain, we took the geometric mean. And now we get to the interesting part, the results. I'm going to show you one graph zoomed in, and then I'm going to show you the graphs for all of the endpoints that we were looking at. So this is our first example graph. It's the acute algae, and it is successful predictions in percent. And unlike in the case with Trident 2, where the chemical space was very large, or the number of chemicals was very large, here we only have a little bit less than 1,800 chemicals, all organic, non-ionizable, etc. And QSAR is able to predict 95% of these, roughly, for acute algae. Vega lands at about 40% in this case, and successful predictions, yeah, I mentioned this. So let's look at all 6 of our endpoints. And it looks like this. We have the acute on the left-hand side, the chronic on the right hand, and then we have algae, Daphne, and fish from top to bottom. And what clearly stands out to us here is in this filtered down data set, QSAR performs the best in terms of successful predictions. I think the average percentage here is around 95. So they are able to produce the most predictions here. TST is only usable for acute Daphne and fish, is a close second. And for all endpoints, Vega has the lowest. The reason for this is Vega is actually producing predictions for almost all of our compounds. But Vega, the software itself, tells us that most of these predictions are outside of the applicability domain. So here we are only allowing within applicability domain predictions. But producing a prediction is not the only thing we need to look at. We also want to look at the prediction error. And here again, an example graph of the acute algae, where we want as low an error as possible, of course. QSAR seems to have a fold change of about 4 in absolute prediction error compared to Vega's at around 7. And for all our 6 endpoints, it looks like this. Vega, the thing that stands out the most to me at least, is the chronic algae model from Vega seems to have quite a high error compared to everything else. But then we can see that TST actually have a slightly lower error than the others, where we have been able to use that. But the chronic Daphne and fish models, the error from Vega is actually the lowest, which is interesting because it's also very few compounds in this comparison for Vega specifically, since the applicability was so low. But this is absolute prediction error. Let's have a look at the correlation between prediction and empirical value. Again, we see an example here, the acute algae model. We're going to see a lot of these, actually. 14 of these graphs shortly. So I want to explain a little bit how they are set up. The dashed line in the middle is a perfect agreement between empirical and predicted values. The dotted lines is a factor of 10 away from the line of perfect agreement. And each point here is a chemical for which we have both a prediction and empirical data. The red line is a trend line that we fitted to this data. And for all of the acute endpoints, we have QSAR, Vega, and test from top to bottom, Daphnia, fish, and algae from left to right. If we look at the top row first, we can see that there's a lot of scatter for QSAR, quite a few outliers when you're comparing the predicted value to the empirical. Whereas for Vega, we can see in the algae model, for example, on the right side, on the second row, that we have fewer data points. But we also see a lower slope of the trend line, which is interesting. And TST seem to have the best agreement between empirical data and predicted, at least visually. For the chronic side, we don't have TST, and we have very little data from Vega. This means that in this comparison, the chronic Vega models, their comparisons or their errors will be based on very little data, sadly. But here we can see, for example, the QSAR fish model seems to have a lot of outliers. And everything that's above the dashed line will be an underestimation of toxicity. And everything below the dashed line is an estimation of toxicity. And we were interested in this pattern, in the trend lines and in the occurrences of over and under prediction. But to look closer at that, we decided to stratify our data. So here to the right, we have the acute algae again as an example, where we assigned classes according to the CLP regulation. In the CLP regulation, there are toxicity classes based on either the EC10 or NOAC and the EC50 values. So, and these thresholds are different from the acute, if you are basing it on acute data, on chronic data for non-readily degradable chemicals or readily degradable chemicals. So we applied this to our data to classify our chemicals. And we ended up with bar charts here, in this case, for the directional error. And the chronic one to the left is the most chronic chemicals. No class to the right are above any threshold in the CLP regulation and the least toxic chemicals. And if we are above our dashed line here, it means that we are underestimating toxicity. And if we are below the dashed line, we are overestimating toxicity. We can see QSAR and Vega in this graph. And for both of these software, on median, we are underestimating the toxicity of the most toxic compounds. This is for one of our endpoints. If we look at all 6 of them, I'm going to give you a little bit to look at these. But it's very clear here that on median, every model is underestimating the toxicity of the most toxic compounds. On the other hand, or at the same time, they are overestimating the toxicity of the least toxic compounds on median. It varies a little bit from software to software and from endpoint to endpoint. But this pattern holds for all of our compared models. We have had discussions about what this might be due to. And the best explanation we have is that the models are erring on the side of the mean of their training data. But this is concerning for many reasons. But before I get there, no, I want to say that now. Because when we are using these models, the things we are most interested in are the most toxic compounds. So to summarize, these models tend to err towards the mean, and this applies to both the simpler models in QSAR, the linear regression models, and also the advanced random forest and support vector machines in Vega. And the toxicity of very toxic compounds is systematically underestimated, and this is concerning when we're using QSARs, for example, for screening. And to reiterate a little bit, or it's that we need these high accuracy models because we have an increasing number of chemicals on the market, and empirical testing is not keeping up. And with that, I see that I went over a little bit, but thank you for your attention. I want to thank my supervisors and also FRAM for inviting me to speak. Thank you very much.